At 20:17:39 Greenwich Mean Time on July 20th, 1969, the lunar module Eagle touched down in the Moon's Sea of Tranquility, approximately 102 hours after launching from Launch Pad 39A at Cape Kennedy, Florida.
9. Ignition sequence starts. 6, 5, 4, 3, 2, 1, 0. All engine running. Liftoff. We have a liftoff. 32 minutes past the hour. Liftoff on Apollo 11.
Excited to leave the module, the crew made the decision to begin extravehicular activities early, rather than wait the scheduled rest time. They radioed this decision in to Mission Control at Johnson Space Center, who responded, "We will support you anytime." At 2:39:33 GMT, the hatch was opened. Neil Armstrong squeezed through and began to descend the ladder to the surface of the Moon, activating a highly specialized television camera as he did so. The signals from that television camera were received by radio antenna in Australia and California, converted, manipulated, and sent to Mission Control in Houston via microwave. From there, the signal was broadcast live to the world. In the US, the footage was distributed by CBS and narrated by Walter Cronkite. All of America and most of the world gathered around their televisions and watched in wonder as a human set foot on another planet for the first time in history. Just before Neil stepped off the module, he looked down and remarked that the feet of the lander had only sunk into the surface of the Moon 1 or 2 inches. That the surface appeared to be made of a fine powder.
At the foot of the ladder, the lamb footbeds are only depressed in the surface about 1 or 2 inches, although the surface appears to be very fine-grained as you get close to it. It's almost like a powder.
Then he took another step and placed his left foot on the surface of the Moon. While Buzz watched from inside the Eagle, Neil radioed a phrase that has now become famous.
That's one small step for man, one giant leap for mankind.
But when Buzz stepped off the ladder a few minutes later, he made his own comment that has largely been forgotten.
Magnificent desolation.
Before this point, the American public had never glimpsed what was beyond the Earth's atmosphere. Perhaps they had seen the science fiction films that were so popular in the 1950s, or shows like Star Trek that had started airing in the 1960s. And featured thriving Earth-like worlds with liquid water and thick vegetation. They had a fantasized idea of what was out in the great beyond. The space race of the 1950s through 70s had also colored the Moon in a political light, as a symbol of democratic superiority over communism, and space itself as essentially a territory over which the US needed to dominate. Regardless of these connotations, the images broadcast live on CBS that day were strikingly dissimilar to Star Trek's Planet of the Week. They were bleak, gray, dusty, alien. It was indeed magnificent desolation. But was that truly all there was? Was humanity really all alone in a big empty universe? Or was there something else out there? Perhaps hiding just under our noses, or maybe just underneath a thin layer of fine powdered moon dust. So, let's start with the basics. Astrobiology is the study of life in the universe, its origins, evolution, and distribution. It is an extremely interdisciplinary field, including aspects of microbiology, geology, physics, biochemistry, and engineering, to name a few. Today, astrobiologists have access to the latest technology, advanced telescopes, space probes, and unmanned submarines that can reach the deepest parts of our oceans. But before we talk about astrobiology today, we have to go back to when it first started. The search for extraterrestrial life began many years before the Apollo 11 lunar module was even built. In truth, humans have been looking up to the stars and wondering what was up there since the birth of our species. During the scientific revolution of the 15th, 16th, and 17th centuries, quantitative reasoning and analytical thinking began to replace the more philosophical method of understanding nature and the world at large. Novel thinkers began to ask how things happened rather than why they happened. Nicholas Copernicus published his heliocentric model in 1538 as an alternative to Ptolemy's geocentric model, which was the accepted theory at the time. He theorized, based on his calculations, that the sun was the center of our solar system, with the Earth and other planets orbiting around it. Ptolemy had posited in his own calculations, titled the Almagest, that the Earth was the center, with the sun and other bodies orbiting around it. Copernicus's theory does a better job accounting for the retrograde motion of planets compared to Ptolemy's theory, and is, as we know today from a variety of other data, the more correct theory. A quick aside. Retrograde motion refers to the phenomena where a planet appears to be moving backwards across the sky. It isn't actually moving backwards, it just looks like it is due to the difference in orbiting speed between it and another planet. This phenomena can be easily understood when we think about things in a heliocentric solar system. If one planet has a smaller orbit than another, then it's moving faster than the planet with the larger orbit. So, as the planet with the smaller orbit catches up and moves past the planet with the larger orbit, the planet with the larger orbit seems to move forward and then backward and then forward again. Essentially, the planet with the smaller orbit is lapping the one with the larger orbit. Thus, they're both moving in the same direction, but one seems to jitter back and forth across the sky. So, Copernicus was correct, but he wasn't completely correct. Astronomists at this time were still relying on what Greek philosophers like Aristotle had told them, and this was that orbits were circles. So, the Copernican model looks like this, with every orbit represented as a circle. The Copernican theory of the solar system was not received with applause and celebration. There was significant pushback from the church on the grounds of theological contradictions, but the scientific community kind of picked the theory apart, pulling out pieces that they found relevant and using them in their own research. So, while Copernicus's main thesis was largely ignored by the community, his calculations helped to establish a stronger footing that the science of astronomy could continue to grow on top of. A great example of Copernican theory being used by other scientists is with Erasmus Reinhold. He used Copernican methods to revamp and recalculate the tables that pretty much every astrologist at the time was using, and had been using since the 13th century. Erasmus's new Prutenic tables were much more accurate than the previous ones, but still weren't nearly as accurate as what we have today. For the big leap forward that came after Erasmus, we have Tycho Brahe to thank. Thanks to bigger and better instruments, Tycho was able to obtain a collection of highly accurate, for the time, measurements of the location of planets and other celestial phenomena. Several of his observations contradicted both Aristotelian and Copernican theory. So, he devised his own system that looked like this. You've probably noticed by now that as technology improved, so did our understanding. Our modern view of the universe was and continues to be built one little step at a time, each time getting a little bit closer to the truth. So after Tycho Brahe comes Johannes Kepler. Kepler is a name that a lot more people are familiar with, at least more than Tycho. Kepler was a mathematician, and he was obsessed with finding the mathematical rules that governed the way our universe worked. Using Tycho's data, Kepler was able to debunk the theory of uniform circular motion, and instead declare that all planets orbit around the Sun in elliptical orbits. This raised the question of what was holding the planets in their orbits. Kepler guessed that it was some kind of magnetic force, a hypothesis that was also described by an English physicist named William Gilbert. Galileo Galilei turned the world on its head in 1610 with his observations of the moon and planets like Jupiter and Venus, revealing them to not be quite as alien as everyone had thought. He revealed that the moon was not flat and smooth, as had been claimed by Aristotle, but was instead rough-looking, with mountain formations. He also observed moons orbiting around Jupiter and the different phases of the planet Venus. While the early questions asked about our universe were focused mostly on understanding its physical dynamics, as time went on and our scientific tools improved, the questions we asked began to change. By the time that men set foot on the moon so many years later, there was already a robust scientific movement underway seeking to answer those new questions. The term astrobiology had been first used by Alfred Russel Wallace nearly 50 years earlier in his book Man's Place in the Universe. Perhaps better known for proposing the principle of natural selection, Wallace explored the habitability of planets in our solar system based upon what was known about their environmental traits. In 1903, he concluded it impossible for there to be life on any planet in the solar system except for Earth. And again, in 1907, he refuted a claim that Mars was inhabitable. NASA, the National Aeronautics and Space Administration, was founded on November 24, 1957, in response to the launch of the Soviet satellite Sputnik 1 in October of that year. The creation of NASA symbolizes the start of the American-Soviet space race, a time when the US and Russia were constantly trying to beat each other to the next scientific landmark. Both of these nations saw the ability to travel to space as a military advantage, and feared that whoever got there first would have the upper hand on the other. For example, the orbit of Sputnik 1 all the way around the Earth caused many Americans to worry that if the Russians could do that with a satellite, perhaps it wouldn't be so hard for them to fire a nuclear missile across the Pacific. In 1959, NASA began its first astrobiology experiment, only a year after it was founded. At the time, referring to the study as exobiology, simply meaning the study of the others. NASA as a scientific organization benefited greatly from the monetary support of the US government and from the fervor of public support sparked by the space race. Never before had humans had the resources to physically leave our planet to explore others. The ability to obtain physical, concrete evidence of life on other planets besides our own has allowed for enormous leaps and bounds in our knowledge of the universe and our understanding of the things that exist within it. The study of astrobiology is strongly rooted in an understanding of how life arose on our own planet. This understanding may be gained from observing fossils, culturing bacteria, developing computer models, or observing organisms that live in the harshest of Earth environments. An equally integral part of astrobiology is the search for environments capable of supporting life on planets besides our own. This may be done by sending technology like landers and rovers, or even humans, to the surface of other planets to collect environmental samples. Unfortunately, this approach is not always easy or even possible to do. The distance that humans can travel in space is limited by our relatively short lifespan, and the fact that we need a lot of things to live, like food, water, and oxygen. Those things take up a lot of space in a vehicle, also limiting how far we can go. At very long distances, conservation of power can severely bottleneck the number of instruments that may operate on board a spacecraft. This makes it difficult to send a large suite of experiments or a large autonomous landing craft to a distant planet. We can get around this issue by designing ultralight, highly streamlined probes that collect images and data at extreme distances from Earth. For example, the deep space probes Voyager 1 and 2 were launched in 1977 and are still transmitting data today, although half of the instruments have now been deactivated on each craft to conserve power. Both probes have now reached interstellar space, approximately 13.4 billion miles from Earth, and are currently collecting data about the composition of deep space. If you'd like to learn more about where each Voyager is or what they're doing, NASA's JPL has a great website that shows each probe's distance from Earth and the status of all onboard instruments. I highly recommend checking it out. Besides probes like the Voyagers, astrobiologists can also use high-powered telescopes, both on land and in space, to find and study planets within and beyond our solar system. Previously undetected planets can be discovered by observing the effects they have on the stars around them, like the dimming of a star as a planet passes in front of it. The Kepler Space Telescope operated just like this, using a method called transit photometry. The Kepler mission was born in 1994 under the name FreeSip, before being renamed after Johannes Kepler 2 years later in 1996. The telescope was launched in 2009 and operated for a total of 9 years. During that time, the Kepler Planet Finder telescope identified 3,924 exoplanets, an estimated 30 of which are similar in size to Earth and are within the habitable zone of their respective stars. Exoplanets of note include TRAPPIST-1e, GJ667cf, Proxima Centauri b, and Kepler 442b, all probably warm, rocky planets of similar size to Earth. Each of these planets is a possible alternate Earth based on their distance from their respective stars, but for now, the most that we can determine about them is their size, approximate temperature, and basic surface characteristics. As our space exploration technology continues to develop, we may soon be able to go further, see further, and learn more about these exoplanets. The Hubble Space Telescope has been in operation since 1990, and the new James Webb Telescope is set to launch in 2021. We may someday be able to visit these planets and study their environments directly to perhaps confirm or debunk the conclusions we have drawn about them using telescopes like these. That day is still quite far off, but we have the tools right here and now to build an understanding of just what makes a planet habitable. By studying the many different biomes of Earth, we can learn a lot about how life has adapted to a variety of environmental conditions and draw some conclusions about what that might mean for similar environments that may not be on Earth. While it can be difficult to obtain details about planets that are incredibly far from our own, we do know quite a bit about the planets within our solar system. Between the 8 planets and 1 dwarf planet that orbit our sun, there are a multitude of distinct environments. Ocean worlds, gas giants, rocky desert worlds, frigid ice planets. Each of these environmental niches could potentially be home to highly specified microbial life. To gain insight into how life may have adapted to survive in these environments, astrobiologists can look at similar environments that exist on Earth and the microbes that colonize these analogs. Astrobiologists on Earth may study microbial diversity at the bottom of the ocean, where temperatures are low and the pressure is high. Or they may research the organisms that thrive in the hot, sulfurous pools of somewhere like Yellowstone National Park. They may even investigate community structure and metabolic adaptations of the microscopic organisms that live in deep subsurface cave springs. There are, within our solar system, certain planets and moons that present higher likelihoods of supporting life. Mars is certainly one of them, but so are some moons like Enceladus and Europa. On this channel, we're going to discuss all of them. We'll talk about the environmental conditions and the history of each, as well as how we know these things. I'll highlight some scientific papers that talk about these planets and break them down so that they're easily understandable. We're going to talk about what we really know about our universe and how we know it.